And we are live. Alright, so right now I'm going to go over how to do the practice problem number 2 in your packet on page 21. If you look over here, you can see the question. A 75 kilogram block is suspended from the end of a uniform 100 Newton beam of length L, which is attached to the wall by an ideal hinge. The support rope is attached 1/4 of the way to the end of a beam at an angle from the wall of theta is equal to 30 degrees. Okay, so there's some actually really important information that isn't labeled on this diagram that I'm going to take the time to do right now. Here's our diagram. The weight of the beam is actually super important. As we discussed today in class, the weight of the beam is going to lie directly at the center of mass. And so what I'm going to do is I'm actually going to label all the forces that were given with a red marker so you can keep track of that. So I'm going to put the center of mass of the beam and show that there's a 100 Newton force pulling down at this point. Now we also know that this mass over here on the far right of the beam pulls down on this end with a tension of, well, we don't know what that tension is, but we know that, well, actually we could figure it out, but we know that it's T1 for now. We also know that this piece of string right over here is T2. We also know this little angle right in here is going to be, I'm going to use an orange marker, it's going to be 30 degrees right in there. Now that's going to be useful in a second, and we'll see why. Now what's really important to keep in mind here is that the axis of rotation is actually right over here. And so what I'm going to do with that is just take note of where that axis of rotation is and just draw in a green X. I know it's difficult to see on this black. The other thing I'm going to do is just take
note of the lengths. The reason why is because whenever we are dealing with a problem involving rotation, we always need to make sure that we're taking into account how far each of these forces are from this fulcrum, or that axis of rotation. So here's one lever arm, here's another lever arm. If you want to review these ideas, flip back to the page right before, and actually a couple pages before when we get to this, in the reading regarding torque, there's some information about what a lever arm is and how that fits into the torques. Anyway, let's get back to this problem. So we want to figure out what the tension is in this support rope, T2. Now, the only way to do this is to first take note of the fact that it's not moving. It's not rotating in this direction or rotating that direction. It's simply staying in position. So that means it's in equilibrium. If it's in equilibrium, we know that the torque net is going to be equal to 0. We also know that the net force is going to be equal to 0. Both of these are useful things to take note of. What I'm going to do is actually establish directions, and this is what you should always be doing whenever you see rotation, is establish clockwise being one direction and counterclockwise being another direction. I'm going to establish that this is positive, this is clockwise is positive, and counterclockwise is negative. All right, so now let's figure out what the net torque, or let's figure out what how we can use the forces that we have to determine the net torque here. Now the way that I'm going to start to do this is just sum up the torques. So torque net that is equal to 0 must be equal to 1. We know that this T1 that's pulling down has to be positive, so T1 plus, and I'm actually going to label this torque 1. Torque 1 for T1. And I'm going to label this torque plus this force right over here. So this is the force of gravity acting on the beam. We know that this torque is also going to pull down in the clockwise direction, so it's going to have a positive sign. T2, on the other hand, is pulling in the counterclockwise direction, so we're going to give that a negative torque. I'm going to call that torque 2, and we know that is all equal to 0. Alright, so now what we can do is start putting some information into these torques. Torque 1 is going to have, remember, torque in general is R times F sine theta. And this is super important because it's going to just be the perpendicular component. Rather than think of it as F sine theta, we should think of it as RF perpendicular. That actually is going to be important here because we have an angle that's not necessarily the angle that we need, but another angle that's given, and we'll see how that plays out in a second. Okay. Oh, I'm already at 5 minutes. Uh-oh. Okay, so T1 is at a distance L. Oh, I didn't draw in the distances. But we'll say that this is at a distance L. This 100 newtons is at a distance 0.5 L because it's half of the length of the meter stick, and this hinge is at a distance of 0.25 L. Okay, now that's useful because right over here we can say, okay, L right over, R is L, right over here, that's the distance away from the axis of rotation. F right over here is 75 kilograms, that's just 750 newtons, because that's what the tension is going to be equal to. That's a tension that's pulling down here. Plus the torque due to the force of gravity, so that's 0.5 L, times F sine theta, in this case 100 newtons, minus, now this is really important, we actually don't have T2 acting perpendicular to the lever arm, right? In fact, it's actually just the perpendicular component of T2. So what I'm going to do is actually draw in a perpendicular component right over here. So this is T2y and then T2x. So the real force that's going to cause a counterclockwise torque over here is actually T2y, not T2 total. So I'm going to write T2 times 0.25 L. So L times 750 newtons plus 0.5 L times 100 newtons minus T2, y times 0.25 L. All right, so now we know that all of this is going to be equal to 0. That's pretty useful because we actually have a lot of information given right over here. We know that there's L in every single expression, so we can actually just get rid of that. And we have a 0 over here and one variable. Easy money, people. Let's take a look. So we got 750 newtons plus 0.5 times 100 plus 50 newtons minus T2y times 0.25 equal to 0. So I'm going to solve for T2y. So T2y is equal to 800 newtons, the sum of these two, divided by 0.25. Now, this is going to be equal to 800 divided by 1/4 is 800 times 4, so 3,200 newtons. Oh no. Sorry about that, my lights just went out. Hey, turn on. Okay, whatever. So we know that T2y is 3,200 newtons. This isn't going to work. So if T2y is 3,200 newtons, then we can figure out T2 pretty easily. If T2y is 3,200 newtons, I'm going to just redraw this over here. I'm going to draw this triangle down here. If we have this angle, we know that this is 30 degrees. We know that this angle has to be 60 degrees. We know that this angle has to be 30 degrees, 90, right? 30, 60, 90. This T2y is equal to 3,200 newtons, and we want to figure out that hypotenuse. If we have this angle and that side, we can definitely figure out that hypotenuse. Let's use a cosine function. So we know that T cosine 30, which is this angle over here, that angle over there, is going to be equal to the adjacent side, 3,200 newtons over adjacent over hypotenuse. Oh, sorry, over T. So then cosine 30 is just adjacent over hypotenuse, so then T is equal to 3,200 newtons divided by cosine 30 degrees. When we do the math out for that, let's see what we get. 3200 divided by cosine 30 should give us around 3695, which is slightly different than the solution that's in the packet, but you know, either or really works. 3695. I think there might have been, yeah, it's probably rounding error between 9.8 and 10. In any case, let me know if you have any questions. This has been an episode of Roy's Physics. I really couldn't think of a more creative title. All right,